Hello everyone. Today we are going to talk about a very important topic. It's about how can you simulate a foundation on pile or by raft on soil using Midas GTS and X. But today we are going to include dynamic loading and liquefaction. As we can see here, this is a model, and this model is created from three layers. The first layer will be the top layer will be non-liquefiable layer from clay, and the base layer is a dense layer, and the in-between layer is a liquefiable layer, loose sand. So in order to be able to simulate such a problem, first thing you will have to know what's the material model you are using. So for the dense sand and for the non-liquefiable clay, you can use more column. But for the liquefiable layer, you will have to use a sophisticated material model called UBC sand. The UBC sand is a very sophisticated material, and it requires a lot of data. Um, in the geotechnical engineering course using Midas GTS and X, we explained in details how you can use this material and what is the parameters and how can you correlate it from different field tests. So once you create your material and you create your problem, so as we can see here, we will have a cap, and this cap will be supported in number of piles. So as we can see here, these piles will be embedded in the dense sand and go through the loose sand. So once you create this, you have to include an interface to simulate the interaction between the pile and the surrounding soil. And you have to input the right boundary condition, which you have to fixate the rotation around the direction. Then you have to include the right boundary condition for the soil. The right boundary condition is you can create it from the free field, which simulate that all these sides is expanded in all direction for infinity. So we can simulate the free field analysis. Then, if you have a live fluid over your cap here, since we are doing non-linear time history analysis, so we have to transfer any load to a gravity load. So from the dynamic analysis, you will have to use load to mass to transfer all the load here to mass. Once you finish creating all your meshing and your for the 3D element and for the 1D element, and you create the plan free field, and you create, as we can see here, and once you create your pile and the interface, so you can now start to create your analysis. First thing in the analysis, you have to create an eigenvalue analysis. Eigenvalue analysis, which is simulating the number of shape models, and you can create or you can find from this the most energy, or which model can give you the most energy, so you can use it for the nonlinear time history. After you create this analysis here, you can find the maximum or the critical frequency, and you can include it in the nonlinear time history. So in the nonlinear time history, you have to include a dynamic load. This dynamic load here, you can choose your earthquake and the duration according to whatever you're interested in. Then you can create your analysis. Your analysis here will be nonlinear time history. And for the nonlinear time history, you include all the mesh and the and the boundary condition, and you include the earthquake. You have to define the time step here, and you have to define the from the analysis control if you are including the in situ analysis for the self weight and using the gravity condition or keynote condition. And you have to clear the displacement from the in situ test, because what concern you is subsequent steps from the analysis. You should cut the negative effective pressure, and if you include you have to include water if you are considering liquefaction. And the most important thing, you have to allow the undrained material behavior. And to allow the undrained material behavior, so you can have excess pore water pressure, and from the excess pore water pressure, you can calculate the excess pore water pressure ratio, which is the main indication for liquefaction state. Then from the dynamic analysis, you have to include the damping method. And from the damping method, you have to, there are different ways. As we can see here, you have to include the mass proportional and the stiffness proportional. We can get this from really analysis. And here you have to include the frequency for the mode 1 and mode 2. Mode 2, this is considered the maximum contribution of the mass, and the damping ratio is 5%. And 5% is just like arbitrary number, and you can't just use it. You have to include free field analysis, or to use this reduction shear stress curves, so you can see the right number for the damping ratio. And you have to consider this for different material, because each material has different could have different damping ratio, if clay or sand. So after this, you can like check the nonlinearity, and now your model is complete after you define your earthquake. But after running the analysis, the time of the analysis is proportional to the number of the steps you including in your analysis. For example, in this analysis, we run like 10 seconds, and each step consider 0.02 second. So we run our analysis for 500 steps. This analysis took around 6 hours on computer 9th generation and 8 processor. The speed of the processor is 3.1 gigabytes gigahertz, sorry. So, and the size of the analysis of this model created a file up to 100 gigabytes. So it's very important to simulate everything in detail, because the time of the analysis can be significant. After you finish your analysis here, we can start to extract the results. As we can see here, this is the results of my analysis, and I can start to see that this is the number of the increment of the analysis, and we can view the minimum and the maximum and the absolute maximum. If we look here at the absolute maximum, we can start to show the displacement, the total displacement or the lateral displacement. Since we are talking about a lateral earthquake, so or a lateral acceleration or lateral acceleration ground motion in x direction, so what concerns me mostly is displacement in x direction. So as we can see here, this is the shape of my model. I can see it deformed and or undeformed, and I can see from here no edge, so I can see my model clearly. And you can see from continuous, this is the output, and you can say it auto range here, so you can see your model. And from probe here, you can start to see the lateral displacement. We can also see here the relative lateral displacement, and from here you can start to see the relative displacement, which is the displacement between the base and the top. So as we can see here, the minimum displacement is 0.1265, and the base displacement is 0, and this is what concern us. So as we can see here, the relative displacement between the base and the top is 12 centimeters. And if I saw here the deformation, as we can see here, So this is the deformation, and we can show here the deformation will be from here, and this is the deformation, and you can see the factor here. We can make it 5 and we apply. So this is the shape of the deformation, and we can go back to 1 and we say apply. So this is relative displacement, and as we can see here, this is lateral displacement between the top and the base. So we can see here that the maximum and the minimum relative displacement is 9 centimeter. And as we can see here at the base, we can see it's 0 and the displacement increases as we go up. So if we just came here and we start to show here the relative displacement, and we can show here the total displacement here, and we can start to see this step by step. So as we can see here, this is our this is my earthquake, and as we can see here that the displacement is increasing with the increase of the motion. So we can see the effect of the size, like when the acceleration in the positive or the negative direction, it affect on the lateral displacement here. So we go back here after we saw the displacement. We are interested to see the bile moments. So I will go here and I only show the bile results, and from the bile results here I will go here to beam element force, and from beam element force I will start to show the bending moment in y direction. So this is the bending moment in y direction, as we can see here, and this is the axial force and the bending moment. And you can extract any data related to the bile from extract, and you go to this here and you choose beam element force, and from the beam element force you can extract the moment from any step, or you can extract just the absolute maximum value, and we select, for example, here this is the pile I'm interested in, and you can filter it and you can just see the table here, and you can also show this in the order of element, and you click table as we can see here, and you can show graph so we can see the maximum bending moment. The same thing can be for the um, for the axial force. I will show again my bicap top base, and I will start here to show the results of the UBC sand, and I will see the excess pore water pressure. When I see the excess pore water pressure here, you can um, rearrange everything here from going to minimum and maximum, and I want to see the range from 0 to this value, and I say apply, and I show only my middle value, and I can see that all of these red values has reached to 1. So if I selected prop here and I went to select, for example, from element, and I selected this one, we can see that this is the excess pore water pressure ratio. Here is 0.8. Here is very concentration for the excess pore water ratio. This is the place of the cap. So we can see this, and we can go back to extract here, and we can go to UBC Sand Results. And from the UBC Sand Results, we can show all the time history of the results. And I see element, and from element, for example, here I can go and I show table. From table here, we can see the time history for the excess pore water pressure to see if the element has reached liquefaction or not. Literature says that if the excess pore water pressure was up to 90% or 80%, we can consider this is triggering liquefaction. The liquefaction is depending on some factors like the number of the cycle and the earthquake intensity and the type of the soil and some other factor. And it's very important to know what causes liquefaction. So as we can see here, this is a built up for the excess pore water pressure, and the excess pore water pressure can drop down at some cycles, and this can be related to the dilation of the friction angle and start to go up again until reaching the maximum value here. And this earthquake can require another cycles to reach to the highest liquefaction or another higher value of higher value a higher value of peak acceleration. Also, we can show here the acceleration amplification. So if we came here and we close this, and here we can just start to show the relative acceleration. Or actually here I'm interested in showing the total acceleration. So if I went back here to show extract, from extract I will pick here accelerations, and from acceleration I don't want to see the minimum maximum, and I will see node or element. So at the base here I expect to see the input motion, so I will start to show table, and from the table here I can start to see the value of the time history of the acceleration. As we can see, it just take a bit, so we are waiting. So sorry, we need to see step, so I'm gonna show it like this. So if we show graph here, this is acceleration value at this point. Sorry, this is a vertical acceleration. I need to see the lateral acceleration. So I'm gonna show table. So once I show table, I can click show graph, and I click now. This is my acceleration. It's very important to see that the acceleration in meter per second square, and so you will have to divide this numbers by 9.81, which is gravity acceleration. So we will go back to our model, and we can start to see values at different depths. So imagine we are getting the value like this here, and we are getting another value like this here, for example, and I am getting another value at the clay layer and another value at the top, and I say table. Well, you can show all the results together to see the amplification on the acceleration or the de-amplification of the acceleration. So as we can see here that my motion start to amplify until the top. So the dynamic analysis is very complicated and it requires a rigorous knowledge about modeling because it has a lot of component. And to be able to do this, you have to know what you are doing and how to choose the parameter. And you have to be well knowledge with the damping and the stiffness portion and mass portion. And the transfer of the load and the nonlinearity of the model and which material model you have to choose, which element of the pile you have to choose. Uh, Midas GTS and X is very powerful software to which you can use it to include very complicated problem, but you have to be well knowledge. If you have if you are interested, you can participate in the geotechnical engineering course using my GTS and X, or we can contact me directly through WhatsApp or my page on Facebook, or you can leave your comment on YouTube. Thank you so much. See you in next video. See ya.